Hello YouTube, this is my first video in my module on calculating measures of central tendency. In this video we're going to focus on the measure of the mean or the average of a data set, okay? So some brief commentary and then we'll get in on notation and vocabulary before we get into a couple of examples. But starting with this, statistic versus parameter. I just want to go ahead and point out the difference between what we mean by a statistic and what we mean by a parameter. Often we hear the word statistic, but we rarely hear the word parameter. But let's consider this, when you're dealing with a large, very, very large set of data, we refer to this as the population, okay? So the population of, say, like, I don't know, if we had like an entire high school or something like that, and I want to know the average age of a student in the high school, we could actually pull out all the data on all of the students in the high school. But let's say our population is quite large. As a matter of fact, we say the number of data, we use an uppercase N to represent this, is, say, like 2,500 students. It might not be that feasible, so what we might try instead is just to do a small sample of students. And so we'd say this represents our sample. Now, we have plenty of sampling methods, but let's say we had a sample of size, say, 100 students. It'd be a little bit easier to work with, and you'll notice here in my sample I use a lowercase n to represent the number of students in our sample is 100. But the very first thing I want to notice is this: there's a difference in notation, the way we write things. When we talk about a population, we want to make it clear to the audience that we're talking about a population, whereas if we're talking about a sample, we want to make it clear we're talking about a sample. So in either case here, I'm saying n equals to represent the number of data, but you'll notice that I've written it a little bit differently for a population than I have for a sample. And the reason why is because, I don't know, consider this: if you found the average age for everybody in the population in, say, this high school, it would be like a perfect number. It would represent the average age, whereas if you represented or you found the average age of the students in this sample, you'd be getting a guess as to what the average might be for the entire population based upon the sample. So if a statistic, we talk about a statistic, we can take a look here. We say a statistic is a characteristic or measure obtained by using data values from a sample. We say a statistic is any measure that we gathered from just using a sample, which is kind of an imperfect picture of the population. Whereas a parameter is a characteristic or measure obtained by using all the data values for a specific population. So we just want to be clear on this. When you actually find statistics for an entire population, we refer to these as parameters, okay? So you can always kind of remember it this way. We say parameter starts with a P. Parameter goes with a population. So it is a statistic about the entire population, whereas a statistic is merely considered something that refers to a sample. And I always remembered this when I went through this, is P goes with parameter, population with parameter, and sample, they both start with S, so they go with statistic here. Okay. So a couple things we'll say about parameters versus statistic. When we talk about statistics, we're always going to use Roman letters to represent the statistics, so like X or X bar. And if you're curious about what we mean by Roman alphabet, this is the alphabet that we use in English, okay? Whereas a parameter, we're going to use lowercase Greek letters to represent parameters. So like mu, this is the Greek letter mu, or this lowercase Greek letter here, sigma, okay? And these would correspond to kind of the things we have up here, X bar and like this lowercase s instead. All right, so we talk about the average. When you hear the word average, it's kind of like saying the most typical case. We say most typical case in a set of data. And remember, this video is to kind of introduce us to measures of central tendency. So it's kind of telling us where the center of data is, okay? But it's found by adding up or summing up all of the data values and then dividing by the total number of data. You notice I use a lowercase letter n here to represent total number of data. So for example, like if we had the values here, 3 plus 2 plus 6 plus 5 plus 4, we would add those all up and get 20 and divide by 5. We would say the mean of this data is 20/5 or 4, okay? And again, like, we had our original data here is 3, 2, 6, 5, and 4. If we were to put this into a data array, which means we'll put this in order, 2, 3, 4, 5, 6, we get the sum of these things, okay, which was 20, and we divide by 4. You notice there that the 4 is kind of in the middle of the data set. So we say 4 is kind of the representative of everybody here. Okay, so in terms of formulas, let's just kind of get a few things out of the way in terms of notation. We say the mean is the sum of the values divided by the total number of values. But we're going to, when we talk about the sample mean, this is important. There's a difference between sample mean and population mean. When we take the mean of a sample, that's our imperfect mean that kind of gives us a picture about the population. So that's a statistic. Whereas the population mean, the mean of like everybody, that would be a parameter. So we're going to write these things a little bit differently, but find them the same way. When you find the sample mean, we use this X bar is how you read this. So we say this is X bar, and it represents the sample mean. But it's found by adding up all of the individual x's, and all these x's here, x1, x2, x3, xn, these are representing our data in the data set. So to kind of drop back to this data set we saw in the first case, we say this is like our x1, it's our x2, we have x3, x4, and x5, where right here we say this is our xn, where n is 5, okay, so we have 5 total data. But it says sum up all the data x and divide by n, and we abbreviate this sum up all the x by using this capital Greek letter sigma. Okay, so we use the capital Greek letter sigma, this is a sigma, to represent a sum, and probably because they both start with the letter s here. But sigma means add up all the x's or the data, divide by however many there are, where n represents, so lowercase n represents the total number of values in the sample. When we discuss a population mean, we're going to use the Greek letter mu, and we use the Greek letter mu, I can tell you, or at least this is a good way to remember it, is because mu starts with m, and so mu and mean, mu, they kind of go together here. But we say mu, whenever you see a mu, we're talking about the population mean. This is actually, we had all of the data in the data set, not missing a single one. So we still add up all the data in the data set here. We go up to x capital N here, and we use a capital N down here. And the capital N, it says it represents the total number of values in the population. So in terms of notation, you see the differences here. We say x bar goes with the sample, whereas mu goes with population mean, but they both mean the mean. So let's go ahead and put these formulas into practice, actually. Got some data sets over here to work with, but we'll talk about a few things we want to get down and good practices here. So let's look at example 1. It says the data represent the number of days off per year for a sample of individuals selected from 9 different countries. So first thing I notice here is we're discussing a sample. Okay. Also we want to find the mean and tell what it represents. So when it comes to finding the mean, of course, we said we need to find the sum of all the data. Best thing to do is actually write this out. We say, what is the sum of all this data? So we'll go ahead and pull out a calculator here, bring it up here. We'll just go ahead and sum this. So we say 20 plus 26 plus 40 plus 36 plus 23 plus 42 plus 35 plus 24 plus 30. And then sometimes if you have lower data sets or smaller data sets, it's good to check your values twice. I happen to know that this is all summing up to 276 here. And since this is a sample, we need to know the total number of data, but we're going to use a lowercase letter n to represent number of things in the sample. And we said that there were 9 countries here, and we can even add this up from our data up here, but we say 9. So our average in this case, since we are talking about a sample, we say is x bar is represented by 276 divided by 9. And so we'll go ahead and pull out our calculator and calculate this. We say 276 divided by 9. Now you'll notice that we get this huge decimal. And so just kind of a good rule of thumb is this, we'll call it the rounding rule. But when you talk about statistics and parameters, but statistics, we could say this, don't round until the last step. And also this, whatever the original data went out to, that is whatever its place value is, these go out to the nearest whole, we'll go 1 extra place value. So for instance here, if this data went out to the nearest whole, we'll go out to the tenths here. So we say 30.6, or 30.7. Well, since this 6 here has a 6 to the right of it, we'll call this 30.7. And we did round, so we want to write approximately 30.7. We want to tell what this represents. So keep in mind this was number of days off per year. So we say days off. We could say per annum or per year. And then this would be our sample statistic. And what it represents is kind of representing where the middle of the data would be. If we were to put this data into an array, that is, put it in order, you would find that 30.7 is relatively in the middle of all this. And also, we say that this is the most typical case. So we interpret the average as meaning the most typical case for a set of data. Okay, so let's try this again. We have a different data set down here where the data represents annual, say, chocolate sales in billions of dollars for a sample of 7 countries in the world. So again, we're working with a sample. Find the mean and tell what it represents. Well, this data set's a little bit different. I wanted to use this on purpose. One reason why is because they've listed the data as in dollars, but only done it once. We're also listing the data here as going out to the tenths. So when we round this, we'll go 1 extra place value. So we say add these data up. First thing we wanted to find was the sum of our data. So we'll clear this out. We say 2.0 plus 4.9 plus 6.5 plus 2.1 plus 5.1 plus 3.2 and lastly 16.6. Holy geez. Okay, so we say 40.4. So the sum of our data, we're listing here with this sigma of all the data, we determined was 40.4, or is 40.4. So $40.4 billion here. And the number of data, since we're talking about a sample, we use lowercase n. We said that there are 7 countries here. So again, our mean will represent with x bar, since we're talking about a sample, is 40 and 4/10. Split 7 ways. We'll get our calculator back out here. We'll divide our sum divided by 7. Another wicked decimal here, but since we're using this rounding rule, it says we'll go out 1 extra place value from what our original data went out to. Since our original data went out to the tenths, we'll go out to the hundredths. So this would be approximately 5.77, and we say billion dollars, okay? And so we want to label this dollars and billions. So if I said, okay, so what does this represent? Again, this is the most typical case. And also it'd be where, kind of the middle of the data is. Now I don't have this data in order, but if you look up top here again, we had like a 2, a 4.9, a 2.1, a 3.2, 5.1, 6.5, but then we had this really large 16.6. So if I were to say, does 5.77 billion kind of describe the most typical case, I'd probably be disinclined to agree with that. And the reason why is because we had a very large number here. So now, without going too much into it, we usually refer to outliers. And these are numbers that are very large, very small, that lie on the outside, okay? And they have a tendency to affect the sum so greatly that it'll toss your average off, high or low. So a good exercise would be like, pause the video, go back and do this again without the 16.6 having been in there. I mean, it would have changed this to a 6 and changed this to 16.6 less, but you'd find that the average is more kind of indicative of what the data really did, okay? So these next 2 examples, we're just going to kind of play around with the formula for the average. Remember, we say the average, or x bar, we'll use x bar here, is the sum of all of our data in the data set over n. We could also call this mu, we say, is the sum of all the data over capital N. Either way we look at this, here's what I want to do. Consider the following situation. Let's say you've taken 5 tests so far this semester, and here are their scores. And let's say these are percentages. What we know is we need to have, like, say, a class average of 85% or above for some reason. The question is, what score do we need to get on the final exam? So what we'll do here is we'll just kind of say, well, if I have a final exam, we'll look at this final exam as being like some other data point here. But since I already know what I need to get on my test here, is an 85% average, what we can do is we can actually substitute this into the formula here. So we'd say 85 would be the average. We say, well, the number of data here, n, this would be, in this case, 6 data. So we could substitute that in down here, and then we'll just find the sum of all of our data. Okay, so, to sum up all of my data here, to write this out the long way, we would say our average is this. We say 80 plus 92 plus 77 plus 78 plus 85 plus x. Okay, let me try to fix that up a little bit here. Plus x, which is our last score, all divided by, in this case, 6. And what we know is we want for this average to come out to be 85. So our job here is to actually just go use some algebra to solve for x. What would we want this test score to be? So the first thing I'm going to do is I'm going to sum up all the data I do know. This is combining like terms here. So we did know that we have so far 80 plus 92 plus 77 plus 78 plus 85. So this is a sum of 412. So what we yield here is this. We say basically 85 equals 412 plus this unknown test score 6 ways. This is what we need. So we'll just solve this. We say multiply both sides by 6. This will cancel out our 6's on the right. And so we get, let's see, 85 times 6. 85 times 6 is, 85 times 6 is 510. So on the left here we have 510 equals 412 plus our single x here, and subtracting 412 from both of these, minus 412, 412. We would get that x, it would imply that x equals a 98, I believe here, 98 if you take 412 away from 510. So what this would mean is our last test here would have to be a 98, 99, or 100, but 98 or above to get an 85 or above in the class. And again, we just found this by summing all the data, including some unknown data value, and dividing by however many there are, and then saying I want this average to be 85. And again, using the formula down here, we say again, x bar, remember it's the sum of all of our data, divided n ways. Let's say in this instance we have a mean of 8 values, so we've averaged 8 values, and we get the average as 76. So I want to know what's the sum Okay, so in this case, we're actually looking for this value here. We already know the average is 76, and we already know the number of data is 8. So we could say this. We'd say 76 is my average that I get when I take the sum of all my data, which I don't know, split 8 ways. And again, it's just algebra. We could multiply both sides by 8 here. And we say, well, then the sum of the data. What was the sum of the data? The sum of the data is 8 times 76 here. So we get 8 times 76 must be 608. And this would be easy to check by plugging back in the 608 divided by 8 and seeing you get 76. So cheers.